Hello guys, welcome to Recitation session week 5 for Water Resources Engineering CEE222. This week we will have 6 different questions again, and the topic is water hammer and pumps. So let me get started with the first question, which is 4.5.3. So let me read the question first. So we have a pipeline here, and inside of the pipeline we have oil, and here, as we can see, we have a valve. The question says that the pipeline must be closed rapidly when a leak is detected, but not so fast as to produce a large pressure rise. So the length of the pipeline is 1,250 meters, and it carries oil, as I mentioned. The specific grade of oil is 0.85, and the bulk modulus of elasticity of water is 1.5 times 10 to the power of 9 Newton divided by square meter. The diameter is 0.5 meters, and it is a steel pipe with expansion joints, which is important for some constant values. And the wall thickness is 2.5 centimeters. The normal discharge under normal conditions is 1.65 cubic meter per second. So in the question, we need to determine the minimum valve closure time that would prevent a large pressure rise. So if we close this valve, a sudden change of flow rate in a large pipeline like this one may affect the large mass of water amount within this pipe, and valve closure or pump shutoff can cause this sudden change, and changing the speed this much could cause a pressure rise, as mentioned in the question, and the pressure could be several times greater than the normal static pressure. So here, this is what happens when we rapidly close this valve. So let's say that we have a flow from reservoir A to B, and once we close this valve, it will cause a pressure wave. So this pressure wave will cause water to go back to the reservoir, and then the pressure wave will continue, and after that the pressure will return back to the valve. So this total time, which is the duration from valve to reservoir and from reservoir to valve, is 2L over C. So that we need to find this value to see if the closure is rapid or not. So we have a condition which you can find on your textbook. So if the closure time is lower or equal to 2L over C, then we can say that this is rapid closure. So this also means that the valve closure is completed before the first pressure returns to the valve. So this duration is so short that it is not allowing water to return to the valve, and this means that we have a rapid closure. But once the closure time is higher than the return time, then we will say it's not rapid closure, and in this question we need to find this minimum time. Okay, so here the C is celerity, which is the speed of wave. and C is equal to composite modulus of elasticity over density within square. And we have another equation that will help us to solve the question. This modulus of elasticity is the function of modulus of elasticity of water and also pipe. So it is equal to EB, which is the modulus of elasticity of water, plus dk. Here d is diameter and k is constant depending on the method of anchoring of the pipeline, divided by EPE. And EP is the modulus of the elasticity of the pipe wall. And here E is thickness of pipe wall. Okay, so in the question, actually we can see that the steel pipe with expansion joints. So here, when we have expansion joints, K will be equal to 1 minus 0.5 Poisson's ratio, and for many pipes it is assumed that it is 0.25. So that from here we will get 0.875 for this constant. So let me write everything we have. So we need to find this composite modulus of elasticity because we need to find C here. After we find C, then we will find the return time, minimum return time, so that we can finish the question. EB is 1.5 10 to the power of 9, and this is Newton over square meter. Then here we have 0.5, which is the diameter. Then K value 0.875 over the modulus elasticity of pipe, and this value is for steel pipe, plus the thickness of the pipe. It is 2.5 centimeters, and in meter it will be 0.025 meters. And this is for steel pipe. Okay, now we have the equation, and from there the AC is 1.32, 9 and 10 Newton over square meter. So here we are just going to substitute this value, which is EC, with the actual value. So let's do that. Actually, I can write here. So C is equal to the value of EC over the density, and density is 998 kilogram cubic meter. Kilogram over cubic meter. Let me write that a little bit above. Okay, better. And also I forgot that since this is not water, this is oil, we need to multiply this density by specific gravity of oil, so which is 0.85. From there we can get the speed of wave as 1250 meters per second. So we found C and we found EC earlier. So now we are just going to use this value here. So let me use another color. So here let me continue with that. So 2L over C is equal to length of pipeline, which is the same with the wave of speed. So speed of wave. So this is giving 2 seconds. So this means that this is the minimum valve closure time that would prevent the large pressure rise. So if we close this valve short faster than this, we will have a rapid closure and it will create the greatest pressure rise within this pipeline. So that it shouldn't be that fast, but we need to be fast to prevent the leakage. But it should be higher than this value to prevent pressure rise. Okay, let's continue with the second question, which is 4.5.5. So first, let me read the question. Here we have 2 reservoirs and 1 pipeline with a length of 1,200 meters. Water flows in this pipeline, and this is the type of the pipe, which is DIP. And the flow is controlled by a gate valve just opposite of the lower reservoir. And you can assume that this is upper reservoir and this is lower reservoir. And the flow rate is 1.35 cubic meter per second when the valve is fully open in this 0.5 meter diameter pipeline with a 2 centimeters wall thickness. And also we have another condition, this pipeline is free to move longitudinally. So based on this, we will have a K value. So we will calculate this based on this condition. So if the valve is closed in 1.5 seconds, determine the maximum water hammer pressure. So if you remember, in the first question, we calculated this valve closure time, but this time it is given and we are going to calculate the pressure. So the water hammer pressure is calculated using this equation, which is the density times speed of wave times initial velocity. And since we assume a 0.25 Poisson's ratio, we can calculate K as 1. So this value will be 1. And now we are going to just write everything we have. composite modulus of elasticity is equal to 1 over oh sorry, this is not the same. It is actually 2.2 times 10 to the power of 9. Okay. Plus we have 0.5. We have 1 here. The EP is 1.6 10 to the power of 11 times thickness, which is 2 centimeters or 0.02 meters. And from that we can calculate EC 1.64 times 10 power of 9 Newton over square meter. And now we need to find the speed of wave, and it contains this EC value, so we are going to just replace it. So density from there we can get C as 1280 meter per second. And now we can calculate the return time of water pressure wave after we close. If you remember from the first question, once we close this valve, it will go back to the reservoir and it will return back to the valve. So this time was 2L over C. So actually in the question we can calculate that as 2 times 1200 over 1280, and this is giving 1.88 seconds. So this is the required time for water pressure to return to the valve after we close. So in the question it is the closure time given as 1.5 seconds, and let me write that here. And since TC, which is 1.5 second, is lower than 1.88 second, which is the required time for pressure wave to return back to the valve, we can say that this is rapid closure. Since we verified that we have a rapid closure, we can directly use this pressure equation, and we are just going to write everything we have. So for density we have 998 times the celerity times the velocity. The flow rate is given as 1.35 cubic meters per second. So we can actually get initial velocity from this initial flow rate. it is 6.88 meter per second. And let me write that. And this gives us 8.79 10 power of 6 Newton over square meter, or it is 8.79 megapascal. So in this question we calculated the water hammer pressure, and this is the water hammer pressure for rapid closure conditions. Therefore we first needed to verify that if it is really a rapid closure condition. So since we have 1.5 second closure valve and it was lower than 2L over C, which is the required time. So since it is lower than that, we said that it is rapid closure. After that, we were able to calculate the pressure, and it is 8.79 megapascal. Okay, let's continue with question 3, and which is 4.5.8. Again, let's start with a reading question. In this question, we need to determine the required pipe thickness of an 8-inch diameter DIP pipe, and this pipe should withstand a water hammer pressure of 250 psi. And here the operational head loss is assumed to be negligible, and the pipeline is anchored at both ends. This is important to calculate the constant K value, and the design flow rate is 1.45 cubic feet per second. Again, we know that water hammer pressure is delta P, which is density, speed of wave, and initial velocity. And initial velocity is Q over A, and it is 1.45 over P. Here we need to convert it to feet. Over 4, and it gives initial velocity as 4.15 feet per second. And from there we actually know the pressures, because the pipe withstands to this value, this psi, 250. So we know initial velocity, we know the density, so we can get speed of wave from this equation. So C is equal to 250 psi, and let's convert it to feet. Over density, and the initial velocity, which is 4.15. Here we can get the celerity or speed of wave as 4470 feet per second. Also from equations, modulus of elasticity equations, we can get the thickness of the pipe wall, but we also know that C was equal to EC over density, so that from here 4470 is equal to EC over 1.94 slug per cubic feet, and this is going to give 3.88 times 10 power 7 pound per square feet, or if you convert it, it is 2.69 times okay. Now we also know the composite modulus of elasticity, and if you remember, we had a formula which is which includes EC, EB, EP, and the thickness. So let me write that. Here this E value is what we are looking for actually, and let me find K value. Since this is a pipe anchored at both ends, we need to use K value as 1 minus Poisson's ratio, and it is 1 minus 0.25 square, and it gives 0.938. And let me write everything here. Since we know EC from here, it is not given here, but we are going to use EB. You can find it from tables. Plus the diameter. This time we are going to use as inch because we write everything in inch. We have K value. And we have EP, which is also not given here, but it is a constant value. You can get it from tables. Times E. And as I mentioned, this is what we are looking for, which is the thickness of pipe wall. And finally, from this equation, we can get E as 0.626 inch. But for operational purposes, you can take it as 0.7 inch. Okay, let's continue with question 4, which is 5.1.3. Here we have a dam in danger of failing, and a pump is needed to quickly drain this small lake behind the dam. So let me draw a pump here. Let's assume that we have a pump like this one, and this pump will drain this lake since the dam is in danger, and it will release to the lake using this pump. The total energy head required to move water over the top of the dam is 2.43 meters. So this height is 2.43 meters, which is from the surface of water to the top of the dam. So basically this means that the pump will suck this water and it will move up to top of this dam, and the height from the surface to the top of the dam is 2.43 meters. And the pump has a 10 centimeters diameter, and it is old, therefore its efficiency is 50%. And here in the question we need to estimate the drawdown, which is how many centimeters the lake goes down. So we will calculate how many centimeters this lake goes down after we drain water using this pump. And we need to find this drawdown within 2 hours. And we also have the surface area here. So let's get started. First of all, we are not able to use pump efficiently because its efficiency is only 50%, so that it will be the actual pump power will be PM, which is 1000 watt, and let me write that. Oh yeah, it's here. And the efficiency is 0.5. This means that we have 500 watt pump. Or this is Newton meter per second. And as you know, the power is calculated using this equation, which is the specific weight times flow rate times height of pump. I mean the head that pump provides. So this is 500. This is 9790 Newton per cubic meter times Q, which we don't know yet, and the head pump head is 2.43. From these calculations, we can get Q as 0.21 cubic meter per second. And to estimate the drawdown, which gives how many centimeters the lake goes down. So drawdown is volume over area. So that per second we have a volume of water as 0.021. So we need to find how many water volume will we have in 2 hours. So if we multiply cubic meter per second by 2 hours, which is 7,200 seconds, over the area, which is 5,000 square meters, and finally this gives 0.0 to 0.0302 meters, or which is 3.02 centimeters in 2 hours. Okay, question 5.1.5. So here we have these two reservoirs, reservoir A and B, and we need to use a pump to move water from A to B. So in the question, it is asked to find the power requirement for a motor that is needed to drive this pump. And the flow rate within this pipe is 2.05 cubic meter per second. And it is a 100 meter long, and its diameter is 80 centimeters. And it is made of rough concrete. And also the water surface of B is higher than A, as 20 meters. And here we have efficiencies for both pump and also the motors. And this is the roughness height of this kind of pipe, and this is the kinematic viscosity. So I think you should remember the energy equation between two surfaces, two reservoirs. So let me write that again. So here we have two missing terms, and of course the first one will be the head loss, because we are moving from A to B, so that there will be some losses throughout the pipe. And the other one is HP, which is the elevation provided by the pump. Since this is increasing the water elevation here, we wrote that on the left hand side. And of course we are going to eliminate some values here. For example, PA with open atmosphere, similar to B. We also have velocity at the surface for A and B. And these are what we have remaining. So let's say this is 20 meters, because the question says that it is higher than A. So this is also 0. And let me continue with what we have. So the total head loss plus 20 meters is equal to HP. And the head loss is minor losses and friction losses. For minor loss, we have two minor losses. The first one is entrance to pipe, and the second one is exit from the pipe. So the entrance is 0.5 and the exit is 1. So that we have 0.5 plus 1 v square over 2g. And for the frictional loss, we have FL v square over 2gd. Okay, so let's see what we know. We know the length, diameter, acceleration. We know velocity, even though we haven't calculated yet. And we need to find friction factor. So let me continue here. So the velocity will be equal to Q over 8 centimeter. From there we can get 4.08 meter per second. And using the velocity and to find the friction factor, actually we can use Reynolds numbers, which is velocity times diameter over kinematic viscosity. Diameter is 0.08 and viscosity is 1.10 to the power of -6. Sorry, this is 0.8. This is also 0.8. And from here we will get 3.26 times to the power 10 to the power of 6. And also we know E over D is required for friction factor, and E is actually 0.6 millimeters, and diameter is 800 millimeters. This gives 0.00075, and from here we are going to use Moody diagram. So F from Moody is 0.0185. Now we know everything in these equations so that we can calculate HP, which is the elevation or water elevation provided by the pump. So let me continue here. So HP is equal to 20 plus V square over 2G or 2 times in the parentheses of 1.5 plus F times 100 meters times 408 square over 2 times over D, because we already used that here, and D is 0.88. From here we can get HP as, let me write here, (23.2 meters). In the equation, we need to find the power requirement for the motors, for the pump, so that we are going to calculate that. And since we need to find in kilowatts, let me clean here. Okay, so in the question we need to find the power requirement for motors that need to drive the pump. So to find the powers, PM or PO, this was our equation, and we have an efficiency. So we need to use efficiency of motor because it is it is the tool that drives the pump. So we use that here. This is specific weight in kilonewton over cubic meter times the flow rate, which is 2.05, and the HP was 23.2 meter over 0.74, and this gives 787 kilowatt. So if the motor has this kilowatt of power, it can pump water as 23.2 meters from A to B. So it is required for this amount of HP.
Yes, let's continue with question 6, which is 5.1.6. Here we have a pump impeller with an outside radius of 50 centimeter and inside radius of 15 centimeters. So here we have 50 and we have 15. And we have vanes or blades with a uniform opening of 20 centimeters. When the impeller is rotated at an angular speed of 450 RPM, water exits from the impeller with an absolute velocity of 45 meter per second. The angle of the exiting water is 35 degrees. So we need to determine the torque generated by the exiting flow. The equation for the torque for the exiting flow is this one, and this is coming from equation of 5.2 from your textbook. Here we have density, we have flow rate, we have radius of the impeller at the exit, we have absolute velocity and cosinus. So let's find what we don't know. First of all, we know density. We know the radius at impeller at exit R0, so RO. We know absolute velocity, and of course, we know the angle. Q is normally velocity times area. But here, since we are dealing with the flow rate inside of this area, we need to convert our terms based on these vanes. So since the cross-section area for the flow is attached to these vanes, we need to use the velocity relative to the blade to calculate the fluid's flow rate. So that instead of absolute velocity, we are going to use relative velocity. And this is relative to blades or vanes. So, and to find that, you can check figure 5.3 from your textbook. So from that figure, let's say this is our absolute velocity, and we will have relative velocity here. Here the relative velocity, which is normal to the cross-sectional, normal to the normal to that cylindrical surface. This value is actually VO times sinus alpha. So let me use that equation here, use that value here. So from here, Q is equal to 45 times sinus 35 degree. This is going to give 25.8 meter per second. Sorry, this is relative velocity. And to find the Q, we need the area times the relative velocity. And when we say area, it will be again the area of these vanes. So that it will be 2p IO, which is the outside radius here. And we have width of vanes, which was 20 centimeters. And of course, times relative velocity. And this is going to give 2p times 0.5, which is outside radius, times 0.2 meters as the width of vanes, and 25.8 meter per second. From this equation, we will get 16.2 cubic meters per second. And since we know the equation for torque, so let me directly write that. So the torque will be equal to density, which is 998 kilogram cubic per cubic meter, times flow rate and times radius. So this is 16.2 cubic meter per second, times the outside radius, times absolute velocity, times cosinus 35 degree. From here, we will get 298,000 Newton times meters, or in other words, it is 298 kilonewton times meters.